See, we discussed this idea that chemical reactions can be categorized into non-redox and redox kind. While non-redox reactions include acid-base displacement, double displacement type of reaction, correct? You could notice the valency factor valency factor in the compounds is determined on the basis of nature of that substance, whether it is acid, base, or a salt. Okay. For example, here it is being salt, its valency factor is 1. Same logic goes to all of them. Okay. A part of it, if you have an acid base reaction, accordingly, you can see an acid is defined, its valency factor is defined on the basis of how many protons it can donate or how many protons or ionizable ions it is able to share. Along with that, when it comes to base, how many OH minus ions it can be sharing, that defines what is the valency factor. Okay. Now, when it comes to redox reactions, right? Now, our objective is mainly to focus on redox reactions. In the case of redox reactions, we need to have two basic things happening. One, an oxidation, and the other one is reduction.
Action.
Correct? By definition, oxidation has, multiple definitions. One simple definition here is, okay, uh, increase in number of oxygens,
Removal
increase
of hydrogen.
number of oxygen atoms in the molecule, correct?
Yes, sir.
Or it can also be defined on the basis of decrease in number of
Hydrogen atom.
hydrogen atoms, hydrogen atoms, clear? Or another way to define is increase in electronegative elements, electronegative elements like fluorine, chlorine, bromine, iodine, like this. Okay, right. These are all very much old and uh, used as per the reaction. But the most generic definition of oxidation includes, okay, uh, loss of electrons, electrons from a species. Loss of electrons from a species is what is the most important point that you need to note if while defining what is oxidation. Okay.
Mhm.
For example, if I say iron Fe, right, is converting into Fe plus 3 electrons. So then I can say iron got oxidized, and this half reaction is called as oxidation reaction.
Mhm.
Correct. I can put it this way also, carbon plus O2 is getting carbon dioxide. Now you can see carbon got rich with oxygen. So I can also use the term that this got oxidized. This got oxidized. And here, now it is not showing about electrons, whether it is one electron, two electrons given, right? So there is something called reduction also, which is happening in this. So we cannot define only oxidation reaction here. I can say that carbon got oxidized, carbon got oxidized. Okay. While if it comes to reduction, reduction by definition, you know that it is about,
Addi-
uh,
uh,
I'll just
Addition of
copy
hydrogen.
that points here. Yeah, because they are very similar points. So instead of increase, this is about decrease. and here it is increase, here it is decrease as well. While the main point of reduction is about gain of electrons, gain of electrons. So for example, if you take O2 plus 2 electrons is becoming uh, O2 or 4 electrons is becoming 2 moles of O2 minus. Then we say this got reduced. We say this got reduced. And this reaction is reduction reaction. Reduction reaction. And the crux is that a redox reaction is both
Reduction and
right,
oxidation.
both oxidation and reduction taking place together. In fact, you cannot have only reduction or only oxidation reaction. If oxidation is happening, reduction has to follow, and vice versa. Got it?
Hmm.
And now, to identify whether a reaction is getting oxidized or reduced, we need to know, right? In fact, we should be able to understand how to, I mean, whether an element is getting oxidized or reduced without actually showing the electrons, without actually showing any idea about how the electrons or oxygens or anything that is being transferred. Okay, that's why we need to we had to come across two important terms. One is called oxidation state, the other one is called oxidation number. Got it?
Yes, sir.
Now it is an arbitrary, okay, charge. It is an developed arbitrary charge developed on an atom when it is removed
Hmm.
when it is removed from all attachments. When you remove an atom from all its attachments, then whatever the hypothetical charge which is being given, that is called as the oxidation state.
Huh. Sir, does that mean all the bonds are broken?
Yes. No, we consider that it is an arbitrary way. That means it is not really happening. That's an easy way of analyzing. That's it. Let me show you with an example. For instance, if you have NH4NO3, okay? Now you know that NH4NO3, if you want to find out what is the oxidation state on this nitrogen and this nitrogen, then what I can say, first we know that NH4 will always convert into NH4 plus and NO3 minus. This is something we must know. Hmm? And next, when it comes to NH4, that means nitrogen is actually making four bonds with hydrogens like this. And overall, it has a charge of plus one. Correct? This is what it meant.
Hmm.
Clear? And now, there are two ways of identifying what is the oxidation state on this nitrogen. Okay?
Hmm.
Here, let's say I have defined that the oxidation state of hydrogen here is 1. Then accordingly, what will be nitrogen? So if X is the oxidation state of nitrogen, there are 4 hydrogens and each one has oxidation state plus 1. Overall, it has plus 1. So X will be equal to minus 3.
That's three. Hmm.
Correct? Now, this way of solving is called algebraic way. algebraic way of solving. That means you create an algebraic equation and then try to figure out what is the oxidation state. Or you can simply judge on the basis of electronegativity, correct? Based on number of bonds we have. For instance, when I write a single line, it always represents that there are two electrons here. Got it? Like this. Now, it depends upon the electronegative difference between these two atoms. Between these two atoms, the power of keeping the electrons is called electronegativity beta.
Hmm.
We'll be learning that in more details as we go ahead. But as of now, you need to know this terminology. What is electronegativity? That is the power of keeping electrons towards itself.
Hmm.
When it comes to nitrogen, it has higher power than hydrogen, which means as it comes to bond breaking, which we just realized defining oxidation number. So this is where I need to break the bond like this, and like this, correct?
Yes.
So when you break the bond here, now I can say that all four hydrogens will come out as H plus because they have lost their electrons.
Hmm.
And now the remaining amount of nitrogen, it has originally it is supposed to have five electrons. Now you see one, two, three, four, correct?
Yes.
But how many extra we have?
Four more.
Five, six, seven, eight. Eight we have, isn't it? So originally it is supposed to have five electrons in the valence shell, but now it has how many? Eight electrons in the valence shell. Got it? And that is been included based on this plus one charge. That's why we can say nitrogen has how many extra electrons overall in the electrons point of view?
Hmm.
Three extra electrons. So that's why we write it as minus three. Okay.
Yes.
Devarshi, does that make sense?
Yes.
Right. So we say now the oxidation state on nitrogen is minus 3 and oxidation state on hydrogen is plus 1. This is another way of writing it over. This one seems much more easier, comfortable,
Yes.
easy to solve. As long as you know the uh, power of elements which can hold the electrons. Likewise, if you compare NO3 minus, now when it comes to the power, oxygen has much stronger power here. So we have N. Structurally, although you may not know the structural way of identifying it, but I'll just writing it for the sake of it. The structurally NO3 minus is like this, but doesn't matter because all we are trying to do is we are trying to adapt an algebraic way. That is, if this is X, then there are three oxygens.
Minus.
Oxygens usually has more power. Each oxygen will try to pull at least two electrons towards itself, and overall there is a minus one charge on it. So that's how it appears. X is plus 5 in this case.
Yes.
So I can say that the oxidation state on ammonia and nitrate in these two cases here, okay, here and here, if I compare, the oxidation state here is plus 5, sorry, minus 3, and oxidation here is plus 5. Correct, beta?
Yes.
These are called oxidation states. See, oxidation state is when you define it for every single atom. But now, when I took this molecule, it has two nitrogens in one molecule, right? In that case, oxidation number can be defined. Oxidation
Number.
number. So oxidation number is the average of all oxidation states.
Hmm.
Correct. Therefore, if you notice here, it is minus 3 plus 5 divided by 2. So how much it is?
Uh,
Plus 1. So plus 1 is the oxidation number -3 and +5 are oxidation states. Okay.
Yes.
Now, generally, generally, oxidation state is, you know, an integer value, while oxidation number
Average
may
value.
be fraction also. Got it?
Yes.
Let me show you with one example. Fe3O4. If you compare this compound, okay. Now, when it comes to the power, oxygen's power is always about pulling two electrons towards itself. So
Yes.
every oxygen will try to get an oxidation state of -2.
Minus
So
2.
use that logic here. In that case, what I will get here, 3 irons into 4 oxygens is equal to 0. So x is equal to 8 by 3, which is a fraction.
Yes.
While there are irons, 3 irons, but the molecule actually formed is from FeO and Fe2O3 together. Now in here, if you calculate, the oxidation state is +2. Here when you calculate, it is +3. So this is oxidation state, this is oxidation state, this is oxidation number.
Yes.
Clear? Right. Okay. So this is one important idea we need to have. Now, what is the main thing that might be missing out to, make sure that you are confidently attempting these type of questions is understanding electronegativity, correct? So if you know based on power of elements that how many electrons it can pull or push, you can arbitrarily start assigning charges much more easily, correct? So that's what we will write it like rules now. Okay. So that is rules of oxidation states. Oxidation states. Now, what are the rules here? See, electronegativity of the elements, if you compare, the highest electronegative element being fluorine, then comes oxygen, then chlorine, nitrogen, bromine, sulfur, iodine, carbon, selenium, phosphorus, hydrogen, boron, beryllium, lithium, sodium, and so on.
Sir.
Okay. So this is like the minimum order we should know. You
Yes.
should be able to see that where hydrogen is, hydrogen becomes more like a bridge between two sides. Before hydrogen, all of them are non-metals. After hydrogen, almost all of them are metals, except for beryllium, of course. Sorry, except for boron, of course. Rest all are being, you know,
Uh,
metals.
sir.
Correct?
Sir.
Yes, Mitra.
This is also given in that type of periodic table, that Lothermier's curve, that on the bottom most electronegative are there and on top.
Perfect. Perfect. Correct. Hmm. So, in a similar lines, you can see from fluorine towards this hydrogen. These are all non-metals, and after that we come across metals. Okay. Now, what is that first thing we need to understand from here is, you know, since fluorine will always win in the bonds, right? Because it is the most powerful one. And how many electrons does it require? See, fluorine belongs to group 17, correct? And its valency already has 7 electrons in the valence shell. It requires only one electron. So just getting one electron, it will be happy, correct? So therefore, fluorine, you can say fluorine, right? Uh, in fluorine present in an element, let me put it this way. Fluorine present in a compound, fluorine present in a compound always shows -1 oxidation state. Okay, other than when it is combined with itself. Got it? So which means if you have F and F, then it is 0. But if it is F and any element E, it is always going to be -1 charge. Clear?
Yes, sir.
Second point, right? Oxidation number or oxidation states of alkali alkali metals alkali metals is always +1. Okay, whether it is lithium, sodium, potassium, rubidium, cesium, it is always going to show +1. Got it?
Yes, sir.
Sorry, I forgot to mention in a compound. Oxidation states of alkali earth metals is always going to be +2. Okay, that includes beryllium, magnesium, calcium, strontium, barium, radium. In fact, francium is also there in the first case, but since it is radioactive and it is not much significant in compounds, I'm not writing that. Okay,
Yes.
next. After this, the next thing we need to assign is about hydrogen. Oxidation state of hydrogen, right, is +1 with non-metals, +1 with non-metals, -1 with
Metal.
metals in general. So in general, we always follow this. For example, if you have NaH, okay, CaH2, got it? And aluminium H3 here, like this, correct? And on the other hand, we also have NH3 here. So in such cases, how do we know what is the oxidation state in these cases? So please check.
If it is metal or non-metal.
Yeah, you just need to check whether they are metal or non-metals. Since sodium is metal here, it will show, I mean,
That's
we know
one.
that it is defined already, it is +1. So hydrogen has to be -1.
Yes.
Calcium is +2, already defined. So here this has to be -1. Aluminium is +3. Hydrogen will be -1.
Hmm.
Now, it is the reverse way to define. Hydrogen is defined as +1. So nitrogen in this case will become -3. Okay,
Yes.
got it? Right. Same goes with water, for example. If you have in water, oxygen is not defined, but hydrogen is already defined. Hydrogen is always going to be +1 and +1, and that makes oxygen as -2. Okay,
Yes.
now oxidation state of any free element, any free element is always equal to 0. Free element or elemental form, sorry,
Hmm.
free element or elemental form. In both case, it will always remain 0.
Sir, what is the meaning of an elemental
I'll
form?
show you. For example, if it comes to metals like sodium, copper, zinc, this is the way they exist, correct? They do not have any combined form, like they both combine and exist as N2, Na2, or copper 2 or zinc 2, like that. But if it comes to phosphorus, phosphorus exists as P4, sulfur exists as S8, okay? Oxygen can exist as, O3 or O2. It can exist in both ways. Understood? And all the halogens exist as F2, Cl2, Br2, N2, H2. Other than that, hydrogens exist in this way.
Hmm.
Correct? O2, I've already explained it.
Yes.
So even when it comes to when it in the combined form, these are called the elemental forms. Okay, they are not exactly element based, but they are in a elemental form based. Hmm? While here, these are simple elemental forms. Got it? Now you might wonder, sir, is it only for metals? Not necessary, even for any non-metals also. Correct? For example, if it comes to selenium, uh, sorry, if it comes to uh, silicon, correct? We can have it in this way. Boron, solid, correct? In fact, boron can exist in simple boron also. It can exist in B12 also.
Hmm.
Got it?
Sir, but
So in
is it
these,
silicon a non-metal? मतलब
yeah,
metalloid. Metalloid.
huh. There are this is always a controversy. The characteristic and the nature of boron is metalloid. Okay, but based on its ionization, electronegativity, correct? Sorry, electron affinity, as well as other factors, they have more mapping towards non-metals. That's why NCRT proposes boron as a non-metal, but it validates all its properties as metalloid.
Hmm.
Got it? But as a definition, if it is asked, because we have to strictly follow NCRT based, so
Hmm.
then you will assume it like a non-metal only.
Yes.
Okay? Right, next. Next. See the sixth one here. The maximum oxidation state, the maximum oxidation number of an element will be its group number, will be its group number in the periodic table, in the periodic table. Got it? And
Yes, sir.
minimum, minimum is always 8 minus the oxidation number. Okay? But again, valid for p block elements only. Is valid for p block elements only. Clear?
Yes, sir.
Hmm. Now, second thing is about oxygen. Oxygen can show variable oxidation states depending on the bonds, depending on the bonds. For example, you have OF2, O2F2. We have H2O2, we have, you know, KO2, we have Li2O, we have Na2O2, we can also have CSO3. All these are various forms of, you know, oxygen existence. Got it?
Yes.
Now let me calculate based on whatever the theory what we learned so far. Oxygen, fluorine is fixed. So if I take X plus 2 times of minus 1, that is equal to 0 because I don't see any charge on the molecule. So in that case, this will become X is equal to plus 2. While here, X plus, sorry, 2X plus 2 times of minus 1 equal to 0. That makes it X is equal to plus 1. While here, if you go on to this side, we have, you know, uh, 2X plus 2 times of plus 1 equal to 0. So that makes X is equal to minus 1. Here we have, 2X plus 1 equal to 0. We are getting X is equal to minus half. So here 2X minus 2 equal to 0. X we are getting it as minus 1. While here we have X plus 2 times of plus 1 equal to 0. So I'm getting X is equal to minus 2. While here 3X plus 1 equal to 0. X is equal to minus 1 by 3. These are all the values which you are getting, beta, in different cases. Isn't it? Okay. Now, when you get plus 2, we usually use this subscript, that is dioxyfluoride. So the naming will always start like this, dioxy. This one is monooxy, correct? Difluoride.
No, no,
Sorry, sorry. First
I
one
have
is
written
monooxy difluoride.
second one is dioxide difluoride.
Hmm. Monooxy difluoride, like this. This one is dioxy difluoride, and so on. Correct? This is the way the name will go. While if the oxidation state comes out to be minus 1, then the oxygen is referred as peroxide, hydrogen peroxide. If it comes to minus half, you call it as superoxide. So potassium superoxide. If it is minus 2, you call it as simply oxide. That means it is lithium oxide.
Hmm.
Here also it is peroxide. Got it?
Minus one by
Here, when it is minus 1 by 3, it is called ozonide. This is
cesium.
called ozonide. So cesium ozonide. Got it?
Yes.
So you could notice that the oxidation number has so many variations, right?
Yes.
So depending upon, how much charge it possesses, with which element it is connected. Now, in general, if you notice that in general, okay, oxygen with any other metals or non-metals, any other metals or
Non-metal.
non-metals, it assumes to have oxidation state, is assumes to have oxidation state of minus 2. In most cases, it will always be minus 2.
Hmm.
Okay, most cases. Only when some cases connected to group 1 fluorine that is given, we have to calculate the way we have done it earlier. Okay.
Yes.
Just knowing the role of oxygen, this table, I mean, this information is sufficient enough to calculate the oxidation of any unknown compounds. Let me show you a few examples here. If you have K2 Cr2O7 and I need to find out for chromium. Now we know this surrounding elements information. That is, there are two chromiums plus two potassiums, each with plus one. Seven oxygens, each oxygen is minus two, overall equal to zero. So 2x is equal to 12. So x is equal to 6. So that is the oxidation state. Correct,
Yes.
beta?
Yes.
Likewise, I can also do it for MnO4 minus, let's say. So I
MnO4
need to calculate it for manganese. So what I can do? So it is x plus
plus
4 times of minus 2 overall equal to minus 1. So x is equal to plus 7.
hmm.
Correct?
Yes.
This is the way I can figure out. Clear,
Yes.
beta?
Yes, sir.
So therefore, if you can just simply calculate the oxidation number, you get to know a lot more information about these elements, their name, how to call their name also. That entire logic will be easier to understand. Clear? Now I'll
Yes.
give you a few compounds. Quickly calculate the oxidation number of various cases. Okay,
Yes, sir.
right. Have a book and pen, and you can start working on it. Find oxidation state of underlined elements. Keep working on it. I'm sure the first one you got it as, I'll just write down the states here. So how much you got? Plus 3.
Oh, I removed oxidation number. Wait a second. Wait a second. Sir.
Ah, okay.
Plus three, plus three, plus three.
Plus 3, yeah. Next one,
6.
plus 6. Next,
3,
plus 3. Right.
4,
Next, plus 4. Right. Chlorine here,
1,
plus 1. Very good. Next one,
3,
plus 3. Next one,
5,
plus 5. Next one,
plus 7,
plus 7. Next one,
plus 2,
plus 2. Next one,
plus 2,
check again. Are you getting
plus,
plus 2?
yes.
See, total we have, let me write down this way. We have total of 4x
5 by 2.
minus 12 minus 2, right? So
5 by
5 by
2.
2. Hmm. So how much you are getting? 5 by 2. So that is the oxidation number. Hmm. Next one, SO2Cl2
6,
plus 6, right? Next one,
not done.
right? See, here, when just like oxygen If by chance nitrogen is also given, by default, if nitrogen is connected with other elements like sulfur or phosphorus or anything else, hydrogen, usually take it as -3 for it. Okay. So if you take that as -3, fluorine is anyway -3. That makes sulfur to become +6.
Yes.
Okay. Here also it is +6. I want you to note down this case beta. Have you noticed something? These are all the ions which are coming from the respective acids. Correct. Now let me tell you what are those acids. For instance, if I write them as HClO, ClO minus with H plus, then that will become HOCl. Here it will become HClO2. This will become HClO3. This will become HClO4. These are the four acids we have. Correct?
Yes, sir.
Usually, if the H plus is being removed, what will it become? It will become a part of a salt, isn't it?
Yes.
Imagine if I treat this HOCl with NaOH, then will it become NaOCl plus H2O.
Oh,
Similarly, if I react HClO2 plus NaOH, if I react that with NaOH, so what will I get? I will get this as
yeah.
NaClO2.
Yes.
So this salt, I mean this ionic form is nothing but a main derivative of that salt.
Hmm.
Correct. So now imagine an atom like chlorine, correct, which is able to show four different type of acids ranging from oxidation state, +1, +3, +5, and +7. If you have these oxidation states, right, the lowest number, whenever you have a +1 oxidation state on the central atom of an acid, the name of that acid should always start with hypo.
Hypo.
It should always start with hypo. Got it? That's why the name of this acid will become hypochlorous acid.
Hypochlorous.
Correct? Now, the next oxidation state does not have that hypo word. So it will simply be chlorous acid. Got it?
Yes, sir.
The next one, if at all you have two highest oxidation state, higher than 4 if you have anything, correct? The highest which is being +7, the +7 should always be used with the term per.
Uh,
So perchloric acid.
hmm.
So wherever you see permanganate, isn't it? That per word is used because of the oxidation state being +7.
7. Always 7.
Always 7. Always 7 मतलब per होना ही चाहिए. Okay.
Hmm.
Next. This time HClO3, now you do not use that per word. You will have this as chloric acid. Okay. Now, notice another second important part. The lower oxidation states usually end up having the name OUS, us acids. The higher oxidation state will always become ic acids.
Yes.
Lower are usually called as us, higher are called as ic acids. Now, how does it start giving a name for this one? So now, every us which is forming, right, OUS, us will always become ITE in a salt form. Ik will always end up become 8. Okay, that is a conversion you need to know. So if you have an acid, conversion to salt, okay, then how does the names change? And us acid will always become ite salt, and ic acid will always become
8. So,
8 salt. Okay,
like hypochlorite.
correct. So therefore, that's why now what is the name for this particular ion beta? This will become hypochlorite ion. Okay. What about this one?
Oh, right.
Chlorite ion. Okay. What about this one?
Chlorate.
Chlorate ion. Right.
Yes.
And what about this one?
Perchlorate ion.
Very good. So this will become perchlorate ion. Make sense?
Yes.
Right. Henceforth, if at all I give you the uh, sorry, list of ions, you should be able to name them as well. Okay. Right. So check this out. The next one, which we can write down, is for this one. You have H2PO2 minus. Okay. H2PO3 minus. H2 next. H2PO4 minus. Got it? In these three cases, we need to check it for phosphorus. In these three cases, we need to check it for phosphorus. And accordingly, you can name it as, what if we have other parts of it? That is, you have HPO3 2 minus and PO4 3 minus. In these cases, the oxidation state will remain the same, but what is the name as well? That's what you need to realize. Check it out. If you can notice these three, they all might be coming from one particular, I mean, they are coming from their respective acids. That is H3PO2, H3PO3, and H3PO4, correct?
Yes.
When it comes to phosphorus acids, these are lower oxidation state acids. This one is the higher oxidation state acid. So the lower one here, the oxidation state is +1. When you solve it, you'll get it. Okay. Similarly, here it is +3 and here it is +5. So in the highest form, we have only one of it. We don't have a per phosphoric acid. Understood? We have maximum phosphoric acid. Therefore, the name wise, if you notice, this will become phosphoric acid, while this will become, you know,
Phosphate.
phosphorus acid, while the first one will become hypophosphorus acid.
Hmm.
Okay? So these are the three names that you need to know. Now, the
Sir,
minute you remove one hydrogen, this will become what, beta?
H2P.
Hypophosphite, correct?
Hypophosphite.
But there are extra two hydrogen, correct? Extra two hydrogen. That's why we have to name that as well. So what do we name it here? Dihydrogen,
Hypophosphite.
correct? Dihydrogen
Phosphate.
hypophosphite. Okay. Second one will become same.
Dihydrogen.
Dihydrogen
Phosphite.
phosphite. Last one,
Dihydrogen phosphate.
phosphate. And what about this one? Only hydrogen. There is only one hydrogen. Hydrogen
Phosphate.
phosphite. Hmm? Because oxidation state is still +3.
Yes. Yes.
What about the last one? Simply
Uh,
phosphate.
Phosphate.
So
Yes.
PO4 3 minus is phosphate. These are all based on the oxidation state. It is being +5. Here it is being +5. Here it is being +3. And here it is being +1.
Sir,
All good?
what is like stopping it from being periphosphoric acid?
The number of valence electrons. Unfortunately, phosphorus has maximum of 5 only. Only if it has 7, it has a chance of giving away all 7 and then becoming +7. Correct? Chlorine, fortunately, has seven of them. Manganese has seven of them. That's the reason chlorine, bromine, iodine, manganese. These are the only elements which can go up to per forms. Okay. Even chromium cannot go because chromium, the maximum number of electrons it has, only six. All good?
Yes, sir.
Right. Okay. Next. Right. These are all, this is the way we need to figure out what are all the oxidation states in this case. Next one. When it comes to figuring out, you know, oxidation states of metals in complexes. In complexes. What are these complexes exactly? These are a different salt forms. Example, I can have K4FeCN6 like this. This is a salt form. Okay. Now in here, if you notice, I need to figure out what is the oxidation state of iron. So what I can do, first, whenever this form is given, I will split them into ionic form. So there are four potassiums. You know that potassiums will always remain plus one, which makes the other part of the complex as overall 4
FeCl
minus.
4
Okay.
Yes.
And now I would assume that the charge of iron is some X. So X plus 6 times of cyanide. Now I need to know this value. That is, cyanide will always possess a minus 1 charge on it, and overall it has minus 4 charge. So X, that's how becomes plus 2. That means the oxidation state of iron in this case is plus 2.
That's true.
Which means these compounds which are large in number, correct? I must know what is the charge they are carrying. Such compounds which are present here, these are called ligands. These are called ligands. These are called ligands. Okay. So now let us see ligand charges. Okay. We just need to know what is the charge they are carrying. It doesn't matter whether, uh, you know, how it has come. We just need to know the charge values. That's it. If you have NO3, it will always carry minus 1. NO2 carries minus 1. If you have N only, it carries minus 2. Correct? If you have NH2, it will always carry minus 1. If it is NH, overall it carries minus 2. Okay? Like this, when it comes to nitrogen, there is one more N3. N3 is called azide. It carries minus 1 charge. Okay? NO actually can carry plus 1 and minus 1, but for our sake, I mean at our level, let us assume only it has minus 1 cases.
Yes.
So these are typically what you will see it from nitrogen side. Sulfur, only sulfur is given, that means it is carrying minus 2 by default. HS is given means it is carrying minus 1. Okay. Sulfate is given minus 2. Sulfite is given minus 2. Thiosulfate, S2O3 is called thiosulfate, minus 2. That is also carrying minus 2. S4O6 is given. By default, it is always going to be minus 2. Okay. These are all about sulfur forms. Carbon, cyanide minus 1. CH3 minus 1. Got it? C carbonate. If you have carbonate, CO3, it will be minus 2. Got it? Oxalate, C2O4, it will be minus 2. Like this. These are all about the carbon ones. Halogens, fluorine minus, chlorine minus, bromine minus, iodine minus. Any form of chlorate, we learned it already. In any form, it will always be minus. Correct? And next comes phosphate. PO4 3 minus. Usually phosphate always carry this part. Got it? And if you have general acids like HCOO always minus. Any RCOO minus, that will always have minus.
Sir, what?
Phenolic group PHO minus, correct? And hydroxide OH minus, hydrogen H minus. Okay.
Sir, what are
Cool.
general?
Huh?
What are general acids?
General acids means if you have any carboxylic acid, RCOOH, it could be any carboxylic acid. If instead of R you have CH3, it is becoming acetic acid. If it is H, it is going to be formic acid and so on. Okay.
Yes, sir.
In the case of oxygen, it could be O minus. If O2 is already given, it can be 2 minus. That means it is peroxide, like that. Okay. There are few terms which by chance it might come. EDTA. It will always carries 4 minus charge. It has a complex structure. We don't have to go through that right now. Okay. If it is been observed, that means it has 4 minus charge.
Okay.
Done. Now, with these combined groups, if I can make any, molecule, you should be able to figure out what is their charge. Now, other than that, everything else is neutral. For example, H2O can act like a ligand. Ammonia can act like a ligand. Alcohol can act like a ligand. Got it? Carbon monoxide can act like a ligand. Right? These are all going to be the neutral ones. They do not have any charge. Let me show you one example. What you are expected out of this list. For example, if at all I have chromium, I have H2O 2 times, NH3, NH3 2 times. I have a cyanide, correct? I have chlorine on it, and overall it is connected to NO3. Now your object is to calculate the oxidation state of chromium. समझ गया ना बेटा? So what you will do, first you will separate them into ions. And you know that it can be written as chromium H2O twice, NH3 twice, cyanide, chloride, overall charge is plus 1 and NO3 will be minus 1. Okay. And now here chromium is X plus 2 times of water is 0, 2 times of ammonia is 0, cyanide is minus 1,
Okay. Am I?
chlorine is minus 1, overall it is plus 1. So that makes X is equal to how much? Plus 3.
Three,
So
yes.
that is the oxidation state of chromium. Was she clear, beta? Very good. So any complex given, in any format given, you should be able to figure out what is the charge that it carries, and accordingly, you must know how much is the oxidation state. Let me give you 3, 4 examples. You can try it out.
Okay.
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 Meanwhile, I suggest just list out all the ligands once so that you are aware of charges what they carry. Okay. Go through it quickly. Write it down. Let me give you a few examples here now. If you have Fe, uh, sorry, NO2 twice, NO2 twice, Cl twice, Cn twice, Cn twice. Overall, we have Na3 here. Now figure out what is the oxidation state on iron. Likewise, if we have K3, cobalt, ADTA, one here, you need to find out what is the oxidation state on cobalt. Okay, sorry, this is K1, not K4. Sodium, boron, hydride. What is on boron here? Next, chromium hydroxide, nitrogen, H2O, thrice, SO4. Right. Try that for chromium. Check these cases. First case, you must have noticed that I can write this entire compound, without the sodium form
Yes.
as overall -3, which makes it x plus 2 times of -1 plus 2 times of -1 plus 2 times of -1 overall equal to -3. So which means x is equal to +3.
Yes. Yes.
Similarly, here
X is equal to
x plus, yeah, 4 times x plus 4 x plus 1 time -4 overall equal to -1. So x is equal to +3. Here
yes.
x plus 4 times -1 overall equal to -1. So x is equal to +3.
Yes.
Correct? So here x plus 2 times of -1 plus -3 plus 0 overall equal to +2. So x is equal to how much? This is
Nine. Oh no, 7.
+7. Clear? Right? This is what we should get. Clear?
Yes.
Although +7 does not exist. Sorry, I'll change it for this case. Make it as manganese, okay? So that we can justify it, that it can get +7 oxidation state. Okay? So these are the ways we need to figure out what are the oxidation states. Right? Now, beta, there are cases where to find out the oxidation state, normal algebraic sum will not help us. Rather, we need to definitely know what is the structure of it. So check out these cases. Calculation of oxidation states by Lewis structures. Okay. Why is this essential also? Let me tell you. For example, if you have H2SO5 and you find it for sulfur, normally what we do, x plus 5 times of -2 overall, sorry, plus 2 overall equal to 0. So what are we getting here? We are getting this as
8.
overall it is plus 8, correct? But that is absurd. Why?
Because
Sulfur does not have any plus 8 oxidation state, correct? So in such cases, we need to know what is the exact amount. I mean, maximum it can stretches up to 6. So how do we know that what exactly is going on here? So for that cases, we need to know the structure. Okay. It's not like we have to do it for every compound. Only for these compounds, structural based analysis is important. Okay. So let us start with that. For example, we'll start with H2SO5 only. Structurally, H2SO5 is like this: S double bond O, double bond O, O and H, and here we have O, O and H. That's how we got it. Okay. Now notice I'm using the electronegative powering here. Okay.
yes.
See, so to find out the oxidation state on sulfur, what will I do? You know that when it comes to sulfur, it will lose one electron on this side. It will lose two electrons on this side. It will lose two electrons on this side. It will
And
lose one electron here. One bond means one electron loss, correct? So I can say how much amount of loss or gain if you calculate it for sulfur. I can say it has loss plus 1, plus 1, plus 2, plus
plus
2. This is the total amount of charge it has developed after losing. Okay. Now from oxygen's point of view, it is gaining from here and here. So this oxygen, if you compare, the oxidation state on this oxygen will be how much? Minus 2. Correct?
Yes.
Likewise, if you notice this oxygen also, the top oxygen and the bottom oxygen, both would have how much amount of charge on it? Both are gaining 2 electrons. So minus 2 and
And
minus 2. Now here is an interesting part. Here this one is gaining 1 electron. But the problem between these two is they fight whatever may be, but they will not lose or gain anything in between them. That's why this oxygen is only gaining minus 1 charge. This one is also gaining only minus 1 charge. So you'll have minus 1 and minus 1. Correct? So which means in H2SO5, this oxygen are normal oxides, while these two oxygens are actually peroxides. So, and there is something called a peroxy linkage here. One oxygen oxygen bond is called as peroxy linkage. Okay, that's the reason why sulfur has plus 6 and not all oxygens are same here. Is that logic clear, beta? Correct. So that's how we need to figure out what is the oxidation state on every element here. Right. See the next example. This is for H2SO5. See the next example. What if you have N3H? This is called hydrazoic acid. Structurally, it is nitrogen connected with double bond, connected with double bond, connected with hydrogen. This is how the structure would be. And the central nitrogen already has a plus 1 charge. This has minus 1 charge. That's how it is getting balanced.
yes.
And now if you notice the charge on them, the last nitrogen is only, it is not gaining anything from the first nitrogen. So it has only minus 1. This does not have any loss or gain from either of the bonds. So this will stay plus 1. Correct? While this nitrogen now has how much beta? It has gain only from hydrogen, because hydrogen, with respect to hydrogen, it will be inflated. So what is the charge it can get? It can have minus 1. And hydrogen will have plus 1 charge. So what are the oxidation states on every nitrogen here? So minus 1, plus 1,
Minus one.
minus 1. Okay. What if I ask you what is the oxidation number? Take the average of these three. So what is the average? Minus 1 by 3.
Yes.
Correct? Clear? Right.
Yes.
So that is based on the structure for these two. See the next one. H2S2O8, which is in a very similar lines of this one. So here we have HO, sulfur, double bond O, double bond O, 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 then sulfur, double bond O, double bond O, and OH. So I'm directly writing the oxidation state. You just check out whether the gain and loss is correct or not. Okay. Here there is huge loss of electrons. Here there is huge loss of electrons. The central ones will remain peroxide, rest will remain minus 2.
Yes.
Correct? Right. So that is the reason why these sulfurs have plus 6 and plus 6. And one peroxy linkage is observed. Next one. H2S2O3. Basically, if you remember H2SO4,
Yes.
H2SO4 structure is very simple. S double bond O, double bond O,
Same.
OH, and
HOH.
OH. This is sulfuric acid structure, beta.
Yes.
Hmm? What we are doing, in this sulfuric acid structure, what if I replace one of the oxygen with sulfur? That's it. I'm not changing its property. I'm only changing the sulfur with it.
Yes.
Okay. Then that will become H2S2O3.
Yes.
Okay. So whenever you replace an oxygen with a sulfur, then you have to specify the name as thio or thio, THIO.
You.
Wherever there is an oxygen which was originally present, उसको निकाल दिया आपने sulfur के साथ replace कर दिया. Then it will become thio or thio. That's why the name here will be thiosulfuric acid. No?
Yes.
Now here is the interesting part. Of course, this will remain minus 2. This will remain minus 2. This will remain minus 2.
Yes.
Along with it, because you have replaced this oxygen, which was originally minus 2, it will retain that minus 2. Even though it is connected to the next sulfur only, electronegativity wise, it observes as if there is no difference, but yet this sulfur will carry that minus 2 charge. And thus, this sulfur will now become plus 6. Clear? So there are two oxidation states available. One is minus 2, the other one is plus 6. So average is how much beta? Minus 2 plus
Plus
6 by 2.
2.
So it's 2. That's why when you calculate, you got it as 2. But that does not mean both sulfurs are plus 2. One of them is minus 2, the other one is plus 6. Okay? Right. See the next one. If you have Na2S4O6, then what is the structural? How does the structure looks like? Notice this one. Here we have sulfur connected to four sulfur simultaneously. And then we have a double bond O, double bond O, double bond O here, double bond O here, one more O minus and O minus.
Yes.
And this total is covered with two sodium ions. That's how we got this way. This is the structure. Okay. Now in here, if you notice the sulfur here is basically, losing two electrons here, losing two electrons here, losing one electron here. So total that makes it plus 5.
Yes.
And same goes with this sulfur, which is plus 5. While this sulfur and this sulfur both will remain 0 because both of them are connected from sulfur ends only. Okay.
Yes.
So what is the name we have here? So this is sodium tetrathionate. This
Sodium.
is called
Acetate.
sodium tetrathionate.
Okay.
These are only based, that's why these are all mainly structural based beta. That's why if you notice, there are two different types of sulfurs here. One sulfur possessing 0 oxidation state, other one having plus 5 oxidation state.
Yes.
Okay.
Yes.
Now, there would be questions that might be asked to figure out, find number of peroxy linkages present. How many linkages are present? Correct? Let me take one example and show you. For instance, I have CrO5. This is the compound given. So what you do, let assume X number of oxygens are peroxide forms. Okay. Then 5 minus X will be oxygens with simple oxide forms. Correct? So therefore 6 And you know that chromium attains how much maximum oxidation state? Plus 6.
Six.
Clear? So when you have, peroxides, usually the maximum oxidation state is adapted. Therefore, you have plus 6 plus 5 minus x times of minus 2, because simple oxide will always have minus 2 charge, plus x times of minus 1, which is peroxide, equal to 0. And from here we got x is equal to 4. So how many peroxy oxygens are there, beta? 4. And 5 minus x, which is 1, which means there are there are 4 peroxy oxides and 1 mono simple oxide, one
One.
simple oxide. Okay.
Okay.
So how do I need to realize the structure in such cases? So check out here. So chromium, one simple oxide means it will always make a double bond. The other 4 oxygens has to make linkages like this. That's how they become peroxide. Okay. This is like a butterfly structure
Yes.
with oxidation state plus 6 here. This is minus 1, minus 1, minus 1, minus 1. So 4 peroxides is always equivalent to 2 peroxy linkages. Done, beta?
Yes.
Can you try few on your own to figure
Yes.
out how is the what is the number of peroxy linkages and all? Right. Try this one. NO4 minus Se2O8 2 minus. All right. So here objective is to figure out peroxy linkages. But let me tell you, nitrogen, the maximum oxidation state it can adapt is plus 5. Selenium can obtain maximum up to plus 6. Okay. So look into the case how we solved it. Do the same before these two. In the case of first one, you can see that x, I can say plus 5 plus, x into minus 1 plus 4 minus x into minus 2 overall equal to minus 1. Correct? This is what I'm sure you should have got it. So we got this as 5 minus x minus 8 plus 2x equal to minus 1. So x will be equal to how much we got? 2 here, correct?
Yes.
So which means the structure should be something like this. Double bond O out of 4, double bond O.
And
Or in
peroxide.
fact, nitrogen cannot have so many double bonds. It is basically dative bond. I'll explain you that later on. This is how the linkage must have been, NOO minus. So which means this oxygen and this oxygen, both of them are peroxy linkages.
Yes.
Clear? Next one. You must have got this as how much? 2 again?
Yes. But
Correct.
ahead of that, the answer.
Yeah. So selenium, just like sulfur, will also have a similar linkage here. Is double bond O with O minus and O minus. So you can see that there is one peroxy linkage here. And here also there is one peroxy linkage here. Okay.
One peroxide. Okay.
What happened, beta?
No, nothing, sir.
Okay. Now, this is the second part of it, which we need to know. Next one is about, identifying the oxidation number on organic compounds. Okay. Oxidation states in organic compounds. We'll start with very simple ones. The first one being, let's say, methanol, CH3OH. Now, basically, here we have carbon with hydrogens here, three hydrogens like this. This is the structure what we have, methanol. Okay. So, what you could do if you want to figure out the oxidation state on carbon, just imagine how many number of electrons it is gaining with, of course, it is slightly electronegative wise greater than hydrogen, but lesser than oxygen. Correct? So that makes it is gaining three electrons and losing one electron. So that makes -2 charge. Okay. Yoshikli beta.
Yes, sir.
Likewise, in case if you have H formic acid, HCOOH, which means the structure is HC double bond O, O and H. Now you can notice from here it is gaining, it is losing two, losing one here. That's why oxidation state now will be one gain and two loss and one more loss. So total +2 oxidation state. Correct? So sometimes the questions would be given like this. CH3OH due to some reactions is converting into HCOOH. Find number of electrons transferred. How many electrons have been transferred? Okay. To find out the number of electrons transferred, so what we can do, the oxidation state here, you can see number of electrons transferred. If you want to find out, it will be here we got the carbon already has -2, and here we got the carbon has +2. -2 to +2. How many electrons are transferred total? 4 electrons got transferred. Okay. You see clear beta? Right. If you have CH3, CH2OH, third one, fourth one, I have CH3CHO. In such cases, figure out what is the oxidation state on each carbon. O and H. Right. Now you know, figure out what is the oxidation state on both the carbons. Likewise, if I gave you benzene with a nitrogen on it like this, and another one nitrogen with double bond O and O minus on this one, like this.
Sir,
So
oh,
to convert from here to here, number of electrons transferred. How many do we have? You need to figure out. Clear? So you need to check out on nitrogen how much it has happened. Likewise, if you have here C double bond OOH, which is benzene converting into CH double bond O. Number of electrons transferred.
Sir, what is that benzene?
See, beta, benzene has no role on it. You just need to notice that these are all the carbons, correct? So carbons identities are not changing. It is a nitrogen which is changing.
Hmm.
So you need to check out how much is the charge earlier on nitrogen. Now how much is the charge? Same goes on this carbon versus this carbon. Can you do that now? Chalo, try that. So let's see what is the oxidation state on this carbon.
-3.
Very good. This carbon.
-1.
Very good. What about this carbon?
-3.
What about this one?
+1.
Right. What about this nitrogen?
Still doing that.
Hmm. Complete that.
For
Hmm.
for the first one, 8 electrons are lost, and for the second one, 2 -2.
So what is the oxidation state on nitrogen here? See,
Minus
nitrogen -3.
yes,
Very good. And what about here?
+5.
+5. Correct?
Yes.
Are you sure it is +5? Check again. See, how many it is losing out?
Mm,
2 it is losing here. 1 it is losing here. 1 it is gaining also, no? With respect to carbon, it is more electronegative.
yes.
So how much it is?
Uh, 3.
3. Correct. So it is +3. So how many electrons must have been transferred? 6. Correct. Now tell me, Devashi, what do we call this process? An oxidation or a reduction?
Oxidation.
Oxidation, because from -3 it is going to +3. So if positive value is increasing, it is always oxidation. Okay. Hmm. Hmm. Clear? Next one. What about this carbon now?
+3.
+3. Very good. What about this carbon now?
+3.
+3. Check again. We have double bond O, loss here, gain here once. So
+1.
+1, na beta.
+1. Yes.
So how many electrons transferred? 2. Again, this is oxidation or reduction?
This is a reduction.
Correct. This is reduction. Done?
Yes.
Okay. Last thing, few structure based in this structure based cases. One last thing which might be asked sometimes is K3CrO8. Okay, structurally it is like this. Chromium having 1, 2, 3, 4, 5, 6, 7, 8. So 8 connections and all 8 are peroxy linkages.
Okay.
And thing here is it is overall -3 charge and 3K plus, which
Uh,
makes the chromium to have a +5 oxidation state. This is a very unique one. It's a very, very unique case. Correct. This is one important case to know. Next one is suboxide. Suboxide C3O2, where we have oxygen connected to carbon, carbon. carbon, then oxygen. It's like a linear molecule here. Oxidation state here is +2, here it is +2, and here it is 0. Got it? Likewise, Br3O8, another important compound, which is completely structure based. These are all only structure based. Double bond O, double bond O, double bond O, double bond O, another double bond O, double bond O, double bond O, and double bond O. So here it is loss of 6 electrons. Here it is loss of 6 electrons, and here it is loss of 4 electrons. Done. These are the other important structures that we need to know.
Mm.
Yoshi, clear beta?
Yes.
Any
Yes, sir.
doubt here?
No, sir.
Right. This is how much you need to know it from